All right, so the second topic for us in the energetics unit is on something called bond enthalpies. Just a little recap about endothermic processes and exothermic processes before we get into bond enthalpies. So whenever you break apart an electrostatic attraction, that is going to require some sort of energy input, right? So anytime you are pulling things apart that are attracted to each other, that takes energy. Okay, so it takes energy to break attractions. Right? That's kind of a key idea. I think it's a pretty intuitive idea, but it takes energy to break attractions. We'll leave it there like, oh, that's just silly now. Alrighty, there we go. Let's fix that. Good. Okay, so a bunch of different examples of attractions being broken is when we break bonds. So if we break a covalent bond, there's just a specific name for that enthalpy. It's called bond enthalpy. If we break apart ionic bonds, we call that a lattice enthalpy. We've already looked at that one earlier in the year, or earlier last year. If we pull electrons off of the nucleus of an atom, we call the Z effective of the nucleus. Well, that's what we called ionization energy, pulling off electrons from atoms in the gas phase. Again, you're breaking an attraction, and that was ionization energies are all positive values. There's also positive enthalpy changes associated with breaking IMFs. So if you melt something, vaporize something, sublime something, there are enthalpy changes that are positive that go along with those as well. Enthalpies of fusion, vaporization, and atomization. And I bolded atomization because it's one that we'll come back to later on. You can pretty much do the converse for exothermic processes, the idea being that if electrostatic attractions are formed between positive and negative particles, when they come smashing together, they end up releasing energy as they become more stable, attracted together. So anytime attractions come together, it releases energy. So that's an exothermic process. So bond formation, whether it's covalent bonds or ionic bonds, is exothermic. If you add electrons to atoms, if you give an extra electron to an atom, it will release energy as it absorbs and attracts in that electron to the atom. And that's actually called the electron affinity. It's another one that we looked at during the periodic trends unit. Forming bonds or forming attractions like IMFs also is exothermic. So freezing, condensing, depositing, those were all exothermic phase changes as things came together and formed attractions. And hydrating something, like when ionic compounds are able to absorb water, so they form attractions with water, that also releases energy. So those have pretty much the same names that we looked at before. And enthalpy of hydration is a specific enthalpy change that we'll look at a little bit later. So when we talk about chemical reactions almost always involve both breaking and forming attractions, usually breaking bonds and also forming new bonds. And whether or not a chemical reaction overall is exothermic or endothermic depends on the magnitude of those different endo and exothermic changes that are happening. Okay? Dissolving is another process that involves both endothermic and endothermic changes happening in succession. And just like with a chemical reaction, when you dissolve something, the balance of those things, the endothermic breaking apart of the ions, and then the exothermic attraction of the water to the ions, the balance of those changes determines whether or not you get a negative or positive enthalpy of solution, which is the name given to the enthalpy change when you dissolve something. And we'll come back to that one a bit more later. So again, just to recap, I'm pointing out that there are certain processes that are endothermic, and they're always when you break things apart that are attracted. There are certain processes that are exothermic, and that's always when things that are attracted come together. And then the net enthalpy change, the delta H, is a balance of those two things. And you have to look at what's being pulled apart and what's coming back together. So one thing that's going to be really important when we talk about enthalpy is something called an enthalpy level diagram. And so an enthalpy level diagram is just meant to sort of illustrate on a graph what's happening in a given reaction. So I'm going to give something a try right now. Let's see how, check that out. We're going to try this. Thank you, Aaron, for hooking me up with this little pen here. We're going to give it a try. I'll try not to screw it up too badly. So that's pretty weird. Whoa, that's really weird. Okay. Sorry, guys. Wow, that is ugly. I'm totally ruining that. So I'm going to actually go away from my little pen for a second until I learn how to use it better. And apologies for that. That was pretty pathetic. But you've got, in any enthalpy level diagram, you're going to have sort of a line that represents reactants, and you're going to have a line that represents products. And the y-axis has to say enthalpy, and the x-axis could just say like course of reaction, or sometimes it says time. So it's not like it has to say seconds or anything, but it is going to show the progress of a reaction. And so the idea is that you start with reactants and you end with products. Those are two key things, but you don't necessarily have to have the products end below the reactants. Sometimes the products, nope, that's my ugly squiggle from before. Sometimes the products will end above the reactants. But the change in enthalpy, let's see, let's get this going on. So the change in enthalpy, and we'll copy that, nice. Check it out. So the change in enthalpy is actually going to be this thing right here. So the difference between reactants and products, that is a delta H. Okay, so that would be for this pair of reactants and products. It's the difference from where you start and where you end. And then if we were instead looking at this combination, then that would be the delta H. Okay. So what I've done is actually really what I was going to do down below here. In an exothermic reaction, your reactants, there's my awesome R, start off with a greater amount of internal energy than the products that you form. And so the change from where you started to where you end up is a negative change. So that's why, one of the reasons why, one of the explanations for why in exothermic reactions you get negative enthalpy changes. Your reactants have more stored energy than your products. And so net, you end up releasing energy to the surroundings. Okay, so there's a bunch of energy in here. The products have less energy inside them. We know that energy can't disappear, so where does it go? It leaves as heat, and it goes to the surroundings and makes things feel warm. Okay, the reverse happens in endothermic reactions. You go from having reactants with less energy inside them to products that have more stored energy. And so the change is positive. There we go, I can do it. Okay, the change is positive. Where does that energy come from? Well, it has to come from somewhere, and it has to come from the surroundings. That's why if you are part of the surroundings and you touch something that's having an endothermic reaction happening, it will feel cold because this heat is coming from you, and it's going into the compounds, and it's being stored up in the products as greater enthalpy, greater stored energy. The other thing that we tend to add to these enthalpy level diagrams is a sort of big curve, a big sort of mountain. And what we're doing is we're representing that reactions have activation energies. It's not just a straight downhill process for exothermic reactions. Many exothermic reactions, pretty much all of them, require some sort of input of energy to get them going. Even very spontaneous reactions like burning methane, burning alcohol, they don't just start on their own. You have to spark them. You have to give them that initial input of energy. That's what the activation energy is. It's the minimum energy required for a reaction to take place. In this next one, you've got this huge activation energy. Okay, so from the bottom all the way up to the top of that energy hill, that is the activation energy. Okay, so both of them have activation energies. Time to move on to bond enthalpies, the point of this video. So average bond enthalpies, or just bond enthalpies, are the enthalpy change required to break 1 mole of a bond in the gas phase. Essentially, it's how much energy does it take to break a bond, but it is measured over a mole of a substance because the energy to break 1 bond is quite small and not really practical. And it's always measured in the gas phase. What happened there? Okay. Oh, I pasted. There we go. This value is averaged for most bond enthalpies. The value that you get in the table is actually an average because the same bond in different molecules might have a slightly different value to be broken. So they measure it over many, many, many compounds, and then they average it, and that's what the average bond enthalpy values are. So bond enthalpies are always positive values because by definition, they are describing the breaking apart of an electrostatic attraction. You look at this little picture of a little hydrogen molecule. Well, the positives are tugging on these electrons, right? Pulling them in towards nucleus and pulling them in towards that nucleus. This is a covalent bond, the electrostatic attraction between 2 nuclei and the shared electron pair. So if you're going to pull these things apart, energy must be supplied in order to do that, okay? Otherwise, there's no way that these things are coming apart, okay? Because they like being near each other. Ways to illustrate these bond enthalpies. If you're going to use a chemical equation, make sure everything is in the gas phase, because that's part of the definition. Bond enthalpies are measured in the gas phase. And just show that 1 bond is being broken. So if this is methane, afterwards, one of the H's is separate. So this is an illustration for the C to H bond, the C to H single bond enthalpy. Right here, this is for the H to H single bond. This one is the O to O double bond, because that's the bond that exists in oxygen. And this represents the N-to-N triple bond enthalpy. So you sometimes get asked to illustrate a bond enthalpy with a chemical equation. And again, it's all about gas phase on both sides of the equation and just showing the bond breaking apart. So going from together as a molecule to going as separate atoms. Okay. Again, the thing about averages, this is just one example or a few examples for the CH bond. Different molecules, you can look these values up online. CH values, bond enthalpy values in different compounds, you can see it actually can vary quite a lot because those neighboring atoms can have an influence. But if you average all the values out for a bunch of different compounds, a bunch of similar compounds, that's where you get this average bond enthalpy. And that's what's listed in table 11 of the data booklet, the average value. When you actually try to do a calculation with bond enthalpies, it's pretty straightforward. You take the sum of all the reactant bond enthalpies and you subtract the sum of the product bond enthalpies. Basically what you're doing is you are looking at the total energy to break all the product reactant bonds, and then you're looking at the energy that you'd get out when you form all the product bonds. And it's kind of as simple as that. The negative sign is in there. The negative sign makes the bond enthalpies of the products exothermic, because when bonds form, it releases energy. The way bond enthalpies are defined, though, they're always positive. So we need to put this negative sign in, and that makes this part the exothermic part, and it makes this part the endothermic part, the energy in part. So if that's part of the reason why whenever you draw an enthalpy level diagram, you always go up first. That activation energy, what is that? Like, why do we need to put in energy? Well, when you want things to react, you first have to supply enough energy to break enough of the reactant bonds to get the ball rolling, to get the reaction happening. So you always draw enthalpy level diagrams with going up first, because the first thing you have to do is break bonds, and that's always positive. Okay. Once you break apart all the atoms, then they can come smashing back together. And when they come smashing back together, that forms new bonds, that releases energy, and that's the negative part. That's why the negative is in there. Okay. So for exothermic reactions, the bonds that you're breaking are weaker than the bonds that you're forming. And so if you put in less energy than you get out, you end up with a net amount of energy being released. Okay. And that means that the delta H will be negative. Okay. And it also means that you're forming stronger bonds. So I mentioned on the enthalpy diagram page that in exothermic reactions, you have products that have less stored energy and they're more stable. Well, part of the reason why they're more energetically stable is that they've got stronger bonds. Okay, so if the products have stronger bonds than the reactants, you get exothermic reactions and a net release of energy. Endothermic is the opposite. It takes more energy to break the bonds than you get back out when you form the products. That leads to a net input or absorption of energy. And so what that means is the products are less energetically stable because they've got weaker bonds. Okay, some final considerations, some limitations. Very common IB questions on this topic. They like to ask you, after you do a bond enthalpy calculation, they then say, okay, well, why is your answer maybe not so accurate? And there's really two things that they're getting at when they do that. One limitation of bond enthalpies is that they are measured in the gas phase. Well, not all reactions happen in the gas phase. So using bond enthalpies for non-gaseous reactions equals very inaccurate. So that's one thing to keep in mind. Always check if they ask you this question about why is your answer maybe not so accurate. Look at the phases of the reactants and products. If you're not in the gas phase, if you have liquids or solids, then it's likely that's a big reason why your answer is not very close to the literature value. Bond enthalpies are really only useful or at all accurate if you're doing reactions that are in the gas phase. The other reason why they tend to be a little bit inaccurate is that they're average values. So they're not specific to the compounds in the problem, in the specific reaction being investigated. Okay. So this is sort of a go-to one. This works whether it's everything's in the gas phase or there's liquids and solids. This is one to consider. Okay, so these are limitations of using bond enthalpies. And we'll end out the video by doing one practice one. I'll see about using the pen, but maybe I'll just wimp it out and I'll use my drawing here. Okay, so this is table 11 in the data booklet. They've got this whole table for single bonds. It's a little funny, but you get the idea in a second. So if I want to know the carbon to hydrogen bond enthalpy, I can find carbon here, and I find hydrogen here, and I go to where they meet, and it's 414 kilojoules per mole to break a carbon to hydrogen bond. I could also find carbon on the left and hydrogen on the right, and they meet there, and notice it's the same value. So it's sort of, each one is listed twice, but it's not that big a deal. Then down below, they also list multiple bonds. So carbon to carbon double bonds and triple bonds, the sort of in-between bond of benzene. They've got the oxygen double bond, the nitrogen triple and double bond. So you have to pay attention to whether or not it's single or double bonds that you're dealing with. So let's see how this works in practice. Calculate the change in enthalpy for the Haber process reaction. Okay, so first off, if you can't draw Lewis structures, well, you can't do this problem. Okay, so really important that you can draw quick Lewis structures, especially for organic molecules, which is why we did some organic before we did this topic. And nitrogen N2, you should remember it's an end-to-end triple bond. H2 is a H to H single bond, and NH3 is like that. Okay. And we did it. Awesome. Okay. So you've got one end-to-end triple bond. you have 3 of these. So it's also important to remember you're going to need to do this one 3 times. You've got 3 N to H bonds in an ammonia molecule, but you have 2 ammonia molecules. So you're going to have to do 6 times N to H. Okay, so we're doing 3 times H to H, and we're doing 1 times N. That's double. So let me fix that, and I'll add a little dealie in there. Cool. So 1 N to N triple. We have to break that apart. We have to break apart 3 H to H bonds. And so those are all the bonds that we have to break. Okay? And then the bonds that we're forming on the right is 6 N to H single bonds. And so I'm going to subtract. This is the energy in, this is the energy input. I have to break these bonds. That's a positive value. And then this is the energy I get back out when I form those bonds. So if I look up in the table above, H to H is 436, and N to H is 391. 436 and 391, and we carry it down here. So 436 times 3. Over here, we got 391 times 6. And if we look up above, the N-to-N triple bond is 945. Okay? So triple bonds are stronger than single bonds, and you can see that clearly right there. So we've got, here's the energy to break that, plus 436 times 3. And so if you added these up, that would be the total energy in. Nope, we don't want that down there. There's our minus sign. And over here, we've got our 391 times 6. So if we plug in the little calculated numbers there, the bonds that we have to break, that adds up to 2253. That's the amount of kilojoules that we have to put in to break all the bonds. Then we subtract out 2346, which is the energy that we get out when we form all those N to H bonds. And so net, you can see that even though that nitrogen bond was super strong, overall, forming 6 new N to H bonds actually gets you out more energy than it requires to break all the bonds. So if you get more energy out than you had to put in, that means it's going to be overall a negative change, which is exothermic. So the Haber process is an exothermic reaction, and the enthalpy change for the reaction is negative 93 kilojoules per mole. So that's one example how you could do these enthalpy change questions. We'll do more in class, and we'll practice some of those limitation questions. Hope that was helpful. And hope I can stop the video.